Hi, in this video, I'm going to go through the OCR A-level chemistry paper. This is the Salters specification, OCR-B. It's paper 1, the 2020 paper, and this is the second half of the paper. I did the first half in an earlier video. Okay, so we start off with a question about halides. The Dead Sea has high concentrations of salt, chlorides, and bromides. Many of the industries use chlorine and bromine as a raw material are located nearby. This avoids transporting these substances. One hazard of transporting chlorine or bromine, I think just say they're both very toxic. That's enough for 1 mark. They're both, well, chlorine is a gas and bromine is a volatile liquid, which will give off a gas, but I think that's enough to say they're toxic. Concentration of bromide ions in water from the Dead Sea is 5 grams per decimeter cubed. Calculate the number of bromide ions and give your answer to an appropriate number of significant figures. Well, that's going to be 1 significant figure because they've only given these to 1. So bear that in mind whilst we're doing it. Okay, so we know the concentration of the bromide ion is equal to 5 grams per decimeter cubed. So let's work out the moles of bromide in 1 dm cubed. That's equal to the mass over the AR of bromine. That is 5 grams over 79.9, which gives us 6.25 times 10 to the minus 5 moles. Okay. Now we need to work out the number of bromide ions. So the number of ions, that's going to be equal to the moles multiplied by the Avogadro constant, L. So that's going to be 6.25 times 10 to the minus 5 multiplied by 6.02 times 10 to the 23. That gives us an answer of 3.78 times 10 to the 19. As we said, we only need to give it to 1 significant figure. So that's going to be 4 times 10 to the 19. Right. Chlorine is obtained by electrolysis. Blah, blah, blah. What happens when chlorine is added to a solution? Describe what you'll see when when chlorine is added to a solution of bromide ions and given the ionic equation. We'll give the ionic equation first. So you're going to get a redox reaction. So you're going to have chlorine, which is a stronger oxidizing agent than bromine. So that's going to take the electrons off the bromide ions to give you chloride ions, and the bromide ions are oxidized back to bromine. Okay, halogen displacement reaction. What are you going to see there? Well, this is reddy brown in solution, whereas everything else is more or less colorless. That's colorless, that's colorless. This is very pale green. So here I'm going to say the colorless solution turns red-brown. Okay, explain in terms of electrons why the reaction takes place. Well, I sort of explained that already a little bit. Well, the chlorine removes the electrons from the bromine. It's got greater affinity for the electrons. The E minus than bromine has because it's smaller. Okay, so the nucleus is closer to the outer shell. This is probably too much for 1 mark, but I'm going to say it all anyway. Sometimes it would be a 2-mark question. Closer to the outer shell of electrons, and also I say there's less shielding. Reactivity of halogens, really. Okay, now here is a big calculation involving some very big numbers. It's not that difficult though. Right. They give us a density of dead seawater. And they give us the concentration of the chloride ions. And we have to calculate the volume of chlorine that's obtained by electrolyzing 1 ton of water. Right, so 1 ton, first of all, is 1,000 kilograms. So that's equal to 10 to the 6 grams. Right. Now we need to work out the volume of the water, first of all. Let's do that. The volume of H2O in 1 ton. Well, that's going to be equal to the mass divided by the density, okay? And these are all in kilograms, so I'm going to leave it in kilograms, okay? The density is there, it's in kilograms for dm cubed. So let's do the so the mass divided by the density. So the mass of 1 ton is 1,000 kilograms. The density is 1.24 kilograms per dm cubed. So that gives us 806.45 dm cubed of water. Okay, so now we would need to do the mass of the chloride ions, okay, in that much water. So mass of Cl minus ions in 865 dm cubed. That's going to be equal to the concentration times by the volume. The concentration in grams per decimeter cubed. So the concentration in grams per decimeter cubed is 208. So we've got 208, and the volume is 806.5 dm cubed, 6.45. That gives us 167,741 grams of chloride ions. Right, now we need to work out the number of moles of chloride ions. Let's do that. Okay, so the moles of chloride ions is equal to the mass over the AR, the atomic mass of chlorine. So that's going to be 16741 divided by 35.5 for chlorine. That gives us 4,725 moles. Now we've got to work out the volume of chlorine gas, okay? So we need to bear in mind there that 2 moles of chlorine, 2 moles of chloride ions is going to give us 1 mole of chlorine gas. So I'm going to say then the moles of Cl2 is going to be that divided by 2. That is equal to 2,362 moles. Now the final step of the calculation I'll do over here. We've got to convert this number of moles of gas into a volume at RTP. Okay, so volume of gas is equal to moles multiplied by, that's in dm cubed. Moles multiplied by volume of 1 mole is 24 dm cubed. So that is going to be 2,362 multiplied by 24. And it does ask us to leave it in standard form. So I'm going to write that down then. So that gives us, work that out on the calculator, you get 5.67 multiplied by 10 to the power of 4 dm cubed. There's our final answer. That's the three significant figures. Okay. Right. Hydrogen chloride can be prepared by the action of concentrated sulfuric acid on sodium chloride, as shown below there. So you've got an acid-base reaction going on there. The sulfuric acid protonates the chloride ion. Right. Explain why hydrogen chloride is a gas at room temperature. Well, I'm just going to say it is a simple covalent molecule. And the intermolecular forces, well, there will be permanent dipole-dipole interactions. Between the molecules. Probably a good idea to say only a small amount of energy needed to overcome those. So that means it's going to be a gas at room temperature. Okay, part 2, show an equation here to show why hydrogen chloride dissolves in water to form an acidic solution. Okay, so hydrogen chloride, HCl, covalent HCl is a strong acid. It will protonate water molecules to form H3O plus ions in solution, which we sort of consider them to be H plus ions normally, don't we? And we'll have chloride ions as well. That would be the equation I would write there, rather than just HCl going to H plus plus Cl minus, because H plus doesn't really exist, of course. It's really H3O plus. Okay, so here we're talking about adding concentrated sulfuric acid to sodium bromide and some of the reaction products here, and we've got to work out the oxidation states. Right, so we won't be working out the oxidation number. The sum of the oxidation numbers is equal to the charge on the species. I'm not going to do them all. I'll just do one as an example. Let's do sulfuric acid, right? So the charge on sulfuric acid is obviously 0. Do this one here, yeah. Oxidation of sulfur in sulfuric acid. That box, sorry. Right, hydrogen is always +1. So there's 2 hydrogens in sulfuric acid. That's +2 for the hydrogens. The sulfur, we don't know. And oxygen is always -2, and there's 4 of them, so that's going to be -8. So simplify that, we get S minus 6 is equal to 0. So the oxidation number of sulfur is +6. So it's going to be +6 there. In SO2 it is +4. Bromine is the uncombined element, so that's obviously 0. And in HBr, well, hydrogen is always +1, so bromine must be -1 there. Right, construct an equation for the reaction of concentrated sulfuric acid with hydrogen bromide. Okay. So we're going to get H2SO4 plus HBr. And that is going to form SO2 and Br2. Right, and we're also going to, some of those oxygens are going to end up as waters. Right, now we need to think about balancing that equation. Look, we've got an oxidation number of sulfur there is +6, and here it's +4. So that means when that goes to there, that has gained 2 electrons. And then we look at the bromine. Do that in blue. The bromine, well, each bromine has gone from -1 to 0. So that's lost 1 electron. So that means to make that balance, we're obviously going to have 2 HBRs. Okay. Now all we need to do is balance. So that's 2 HBRs for every 1 sulfuric acid to balance the electrons. Now we need to think about how many oxygens. Well, we've got 4 there. We've only got 2 in sulfur dioxide, so that means we must have 2 waters. And then if you check the number of hydrogens there, that's all balanced. So that's the right answer, the balanced equation there. Okay, onto organic chemistry now. Chloroethene is made in 2 steps. All right, so you form the dichloroethane from ethene, and then thermally crack it to eliminate HCl. Give the repeat unit of polychloroethene and the type of polymerization taking place. Right, so that's pretty straightforward. Right, so we're going to have chloroethene. Let's draw it like that. We'll draw another chloroethene next to it. Right, what happens when it reacts is you're going to form a new bond between those 2, and you lose the double bonds there, don't you? Okay, so let's draw the repeating unit then. Just rub some stuff out there. Right, so you're going to have that goes like that. We just square bracket. That's the repeating unit. What kind of polymerization is it? It was addition polymerization. It's not condensation polymerization, which is the other kind we've come across. It's addition. Okay, the HCl produced in step 2 can then be used to make more chloroethene by reaction with ethane, here with a triple bond in it. Okay, suggest the mechanism for the reaction of HCl with ethane. Well, this is going to be more or less the same as the reaction of HCl with ethene, which you are familiar with. So we just kind of extrapolate that knowledge. So here we've got a triple bond between the carbon. That's going to be attractive to electrophiles. There's only 1 hydrogen attached there. Right, so here is our, let's do our HbHCl. Right, we've got a dipole on that. That's delta positive because hydrogen is less electronegative than chlorine. That's delta negative. Right, the first step in the mechanism is for one of the pi bonds there is to break and to go onto the hydrogen. And the hydrogen chlorine bond is then going to have to break. Both electrons go to the chlorine. So we have then got this intermediate. Let's draw it. So we've got 1 hydrogen there. We've got the new hydrogen, which is, I'll do that in red. That's come from the HCl. We don't have a triple bond anymore. One of the pi bonds is broken, so we've just got a double bond. And we've got 1 hydrogen attached to that carbon, and that carbon is going to have a positive charge. It's only forming 3 bonds. That's one way of sort of working out it's got a positive charge on it. That's not a partial positive charge, that's a full positive charge. It's a carbocation. That is then going to react with the chloride ion. We draw a lone pair. We've got 4 lone pairs in the chlorine. We only draw 1 of them. And that lone pair is then going to go onto that carbon to form the final product, chloroethene. So we've got H there and Cl there. Okay, so right, give the systematic name for this stuff here. Well, we've got it's ethane, 2 carbons long, saturated. You've got 2 chlorines on it, 1 on number 1, 1 on number 2, so it's 1,2 dichloroethane. Okay, the dichloroethane can be converted to the diol. So we are swapping a chloride, the chlorine atom, for an OH group by refluxing with sodium hydroxide. What kind of mechanism? Well, that's nucleophilic substitution, isn't it? You've got the OH minus there, remember, you've got a delta positive on that. That's going to go onto there. So it is nucleophilic substitution. Okay, so the bit more polymers now. The diol here can be reacted with a dicarboxylic acid to make another polymer. Complete the equation for the reaction below. Right, we're going to form a diester here. We're going to form esters. Okay, so we're going to lose water there. Okay, and it's the same thing is going to happen at this end as well. Okay, so we are going to form, let's draw the repeat unit of the polymer. Right, so first of all, I'll just draw that draw this like this first of all. CH2, CH2. Now here we're forming the ester now, so that's going to be O, and then we've got benzene ring, and we've got the carboxylic acid at that end. Well, that's not quite complete yet, because of course at these two ends the same thing is going to happen. Right, so we're going to lose that there. That's going to form an ester to the next one along. So I'm going to put my square bracket there, and that's going to happen at this end as well. You're going to lose that there. So make that a bit neater. That one is going to form the ester. Right, that's our repeating unit. That one's a condensation polymer, of course, compared to the last one, which was an addition polymer. Okay, propene is produced in a cracking reaction. Propene can be reacted with benzene in the presence of oxygen to produce two useful products, A and B. Right. So you're going to react propene which is like that, plus benzene, and some oxygen, and that's going to make these two products A and B. We've got to decide what they are. Right, so on product A, so you add a bit of universal indicator and you get an orange color. Now that's telling us that it is very weakly acidic. It doesn't react with sodium carbonate here though. So that is telling us that it is very, very weakly acidic. It is not a carboxylic acid. It's not sufficiently acidic to be able to react with sodium carbonate. So that means it can't be a carboxylic acid. So we've got to think, what organic functional group is very weakly acidic, but isn't a carboxylic acid? Well, and you've got a benzene here as a bit of a giveaway. Hopefully you realize that we're talking about a phenol functional group there. Okay, that's a phenol functional group. Which phenol we don't know yet. And this is confirmed by this other test here. Look, when you add neutral iron to chloride solution, the phenol forms a complex ion with the Fe3 plus. Right, the oxygens on the phenol, the lone pair on the oxygen forms a dative bond to that. You form a complex ion, and that complex ion is purple color. It's a bit of a useful test tube test for a phenol. So we can definitely say we've got a phenol in product A. It gives us some more information. We've got to find out which phenol, right? So it gives us a mass spectrum of product A, right? And we can see here that the MZ of the parent ion, I think there is 90, is that 94? It's 94, I think, yeah, that one there. So the MR of this compound then is going to be 94. So we're looking for a phenol with an MR of 94. Well, if you just look at that phenol itself, right, that's going to be C6H6O, and that's got an MR of 94. So that's what we've formed. We have formed just phenol itself. Now we need to look at what product B could be. Okay, so we form phenol, product B. Now don't forget what we're adding here again. We're adding propene, propene to benzene, and we need some oxygen as well there. Okay, so this product B stays green. It is neutral, so it's not a carboxylic acid, it's not a phenol. Test with Tollens reagent, no change seen, so it's not an aldehyde. React with sodium borohydride, it's reduced to an alcohol. Well, that tells us it is a, it must be a ketone then. Okay, so it must be a ketone. In other words, it's got to contain this sort of functional group. Right, we don't know which ketone, but they give us the percentage by mass here. So let's work that out. What have we got? Right. I'm just gonna, so I'm gonna get rid of that, give myself a bit of space because we'll be answering that question. Let's do this then. So in 100 grams, we're going to have 62.1 grams of carbon, 10.3 grams of hydrogen, 27.6 grams of oxygen. So let's do the moles then. So we're going to do the moles. I'm going to divide by the AR. So that's going to be 62.1 over 12, 10.3 over 1, and 27.6 over 16. So that gives us 5.175 moles of carbon, 10.3 moles of hydrogen. So we see probably got a 2-to-1 ratio going on there. And finally, 1.7 moles of oxygen. So we're going to divide by the smallest number there, which is 1.75. So that gives us 3 to 6 to 1 ratio. So the empirical formula of the compound is C3H6O. And we have established that it is a ketone. So do we know any ketones with that formula? Well, there's only one. That's going to be propanone. So we can safely say, I think, that compound B is propanone. So we get phenol and propanone, the two products of that reaction. Okay, so this is about diazo dyes, this question. Okay, they want to bind, they want to synthesize dyes that will bind well to wool fibers. So they're going to react, coupling reactions between a phenol and a diazonium ion, okay? The student synthesizes dyes C in 2 steps, right? The first step, he's making the diazonium ion in this step, isn't he? So he's reacting phenylamine with sodium nitrite and HCl. Okay, now what conditions do we need for that? We need to carry that out on an ice bath. Otherwise, the diazonium ion that you form is going to will break down. We need to write the product as step 1. What's the product there? Well, that's going to be nothing happens to the benzene ring, but that nitrogen is now triple bonded to another nitrogen, and we're going to have a positive charge on that nitrogen. That's the diazonium ion, and of course that comes with a chloride ion from the HCl. So that is the product. It's step 1, and that diazonium ion is going to react in a coupling reaction in the next step. So they get the diazonium ion, and they form di-C. So I'm going to draw the diazonium ion there. Okay, so we can see that that diazonium ion is that part of the molecule has come from the diazonium ion. So the reagent for di C is just going to be simply, it's going to be that bit there, right? It's called, so let's draw that. So we've got these two 6-membered rings stuck together. Okay, now we need to get the bonding right there. So you have a double bond there, double bond there, double bond there, there, and there. And we have the OH group stuck on there. Okay, so that is the reagent required for step 2. This, of course, is an electrophile. Didn't ask you this, but that's an electrophile. And so that is going to attach, that's going to attack the blue compound, the naphtol here. Going to get electrophilic substitution reaction occurring there. Okay, di C can be converted, a bit bigger, I think. There's di C. Di C can be modified to form di D, shown below. So what have they done there? They've stuck this SO3 minus group on it. Okay, how do you do that? How do you stick an SO3 minus group onto a benzene ring? So the reagents and conditions you're going to need, you need to reflux with conc sulfuric acid. And you get an electrophilic substitution reaction occurring there. Heat and reflux with conc sulfuric acid. Right, comment on the solubility of the two dyes. Well, let's just look at di C. Now, what is solubility in water? In water, that's important. Okay, now, which is going to be the most soluble of those in water? Well, I'd say di C is not going to be probably not too soluble in water because it's got lots of groups in it which are only really going to form London forces, and there's not going to be much. Well, I suppose this can form H bonds, yeah, but that's only a small part of the molecule. Di D is going to be much more soluble because it's got a charged group on it there. Okay, charged things dissolve well in polar solvents, so di D will be more soluble, so it might be more useful than di C as a result of that. Okay, so there we go, 4 marks. Okay, consider intermolecular bonds and their relative strength. Solubility of di C. All right, I would say probably mostly London forces. And they're weaker intermolecular forces. Water doesn't form London forces very much. Okay, so it's not going to be very soluble. Solubility of di D, well, the SO3 group is charged, so the water molecules are going to be interact with that, and they're also going to be able to form H bonds to those oxygens on the SO3 group, H bonds, and they are stronger intermolecular forces, and water can form them, so it's going to be more soluble. Okay. Right, di C has an orange color. Explain why di C absorbs visible light. Okay, well, first of all, you have got an extended you've got an extended delocalized electron system, okay? Or conjugation, if you want to call it that. Why have you got that? Well, you've got all the electrons, right? You've got, don't need to say this, but you've got unhybridized pi electrons on all of these carbons here, every single carbon. You've got them on those nitrogens as well, and all the ones on the napsol ring. Okay, so all of those electrons are all delocalized. And what happens is you can absorb energy. Those electrons can absorb visible light, absorb radiation in the visible part of the spectrum. The energy is given by, I'll write down the equation because I think that will probably be required, by HF, where F is the frequency of the light, E is the energy, and H is Planck's constant. Okay, so you're going to get, it will absorb energy and promote those electrons to a higher energy state, the delocalized electrons. And so that's why they absorb it. Now, how is the color of the light absorbed related to the light seen? Well, white light, I would say that white light is a mixture of all the colors. Okay, only some are absorbed. And you see, the color you see is the color of the light that is not absorbed. The frequency of the light not absorbed. Okay. Right. Wool is based on protein structure. Wool is keratin, a protein. Explain how dye D might bind to the wool fibers in weakly acidic conditions. Okay, so I think it means weakly acidic. So that means that it's not strong. This is quite a strong acid, so there's not enough to protonate that. So that's still going to be negatively charged there. But don't forget, on proteins, you have side chains. You have NH2 groups on certain amino acids, which under weakly acidic conditions will be protonated to NH3 plus. Okay, that's positively charged, and that is going to interact with the negatively charged group there. That's all you need to say there, I think. So protonated NH2 side chains on the protein, NH3 plus positive, interact with the negative part of the dye. Right, the students have some wool samples that have dyed. They wanted to find out how much of the dye washes out of the wool at different temperatures, and they decided to use colorimetry. Describe a suitable method, include the control variables in your answer. Okay, so what they're probably going to have to do is, right, they're going to get equal. Or what they're changing the temperature, aren't they? Okay, so they're going to get equal masses of wool. That's a control variable. And they're going to wash them for the same time. In the same volume of water. They're all the control variables, but at different temperatures. Okay. And then they're going to collect the water that's been used for the washing, so filter out the wool. And now they're going to have to analyze that water in a colorimeter. They're going to measure the absorbance of those samples. But what we're going to have to do is, how do we relate that absorbance to an actual concentration of dye? Well, they need to make up a calibration curve. So how do you do that? Well, you get known concentrations of dye. Measure the absorbance of each one. In the colorimeter. And use that to plot a graph. On the graph, you're going to plot absorbance on this axis against concentration. So you're going to get a curve like that. Draw a line of best fit. And then how do you find out the concentration of the dyes of the samples? Well, you measure these absorbances of these samples here. You know the concentration, the absorbance there. You interpolate the graph to find out the concentration of the dye. I think that's all you need to say for your 6 marks there. Okay, some new question now about finding the concentration of chloride ions in seawater. They're going to use a titration method. They dilute the seawater and then titrate with standard silver nitrate. Okay. Ooh, right. Right. They dilute the seawater and titrate with standard silver nitrate solution. Describe what's observed when silver nitrate is added to the seawater and give an ionic equation. Well, I'll give the ionic equation first. Well, silver nitrate contains obviously Ag plus ions in aqueous solution. And the seawater contains chloride ions. In aqueous solution. And they are going to precipitate out to form AgCl solid, which is a white precipitate. Okay, so that's what you're going to see. Part A, you're going to see a white precipitate forming, and the precipitate will be of silver chloride. Right, here's the method they use then. The students first dilute the seawater by pipetting, so drawing little pictures here, 20 centimeters cubed of seawater, and they put it into a volumetric flask here, and they dilute it up to 100 centimeters cubed, so that's like a 5-fold dilution, isn't it? Right, and then they're going to take out 25 of that, and they're going to titrate against silver nitrate over here. And we know the concentration and we know the titer. So let's work out the moles of silver nitrate we've got first of all. Let's do that. So moles NaAgNO3 in the titer is equal to conc times volume. So that's going to be 0.1 multiplied by 26.5 over 1,000. And that is equal to 2.65 times 10 to the minus 3 moles. Now, as we saw in the equation before, the Ag plus ions react with the chloride ions in a 1-to-1 ratio. So we can say from that, like the moles of chloride in 25 centimeters cubed. 25 centimeters cubed there. Is the same. Right, 10 to the minus 3. Right, that is only in, of course, 25 centimeters cubed. How much of that do we have here? We've got 100 centimeters cubed, so we multiply that by 4. Let's do that. So moles of Cl minus in 100 is equal to that multiplied by 4, which is equal to 0.0106 moles. Right, looking at our diagram, that is in diluted seawater, right? Right, that's in the, we've got 0.0, let's write that down there. So we've got 0.0106 moles in there. Right, so that means what is the concentration of the of those ions in the original seawater? Well, that all of that 1.6 moles, all of that came from 20 centimeters cubed of seawater. So the concentration in seawater is going to be moles over volume. So that's 0.0106 divided by 20 centimeters cubed, 20 over 1,000. That gives us an answer of 0.530, to 3 significant figures, mole per decimeter cubed. So there's our answer there. Right. Right, now what do they use? This is about how they use an indicator for this. They use potassium chromate as the indicator. Now, how does that work? At the endpoint, all the silver chloride has been precipitated out, and you've got a slight excess of silver ions. Okay, and that is then going to precipitate out with the chromate ions to form this red-brown precipitate. So the endpoint, you're looking for this red-brown. So you've got to wait for all the silver ions to have been used up by the chloride ions. And once all the chloride ions have gone, a tiny bit of Ag plus will remain in solution, and that will then precipitate out with the chromate. Okay, so that's what we're thinking about. Now, the solubility product of silver chloride is this, okay? And use this value to explain why the concentration of Ag plus ions at the endpoint is going to be that, okay? So we say, yeah, silver chloride is completely insoluble. It's not completely insoluble. So there's always a tiny bit of it which remains, okay? So what's the equation for the solubility product here? Well, we've got, let's write down the equation. So we've got Ag plus and Cl minus going to form AgCl. So the solubility product in this case is going to be the concentration of the Ag plus ions multiplied by the concentration of the Cl minus ions. We're going to say, right, that they're equal to each other at the end point. So that simplifies out then that the KSP is going to be equal to Ag plus squared. So how do we find out the concentration of Ag plus ions at the equilibrium position? Okay. That's going to be the square root, the KSP, which is the square root of 1.41 times 10 to the minus 5. And that is equal to, sorry, the square root of 2 times 10 to the minus 10. And that is equal to 1.41 times 10 to the minus 5 moles per decimeter cubed, which is what we sought out to show in the first place. Okay. Right, now the next bit, right. The solubility product of silver chromate, right? They give us the equation for it. Of course, it's Ag plus squared because the formula of the precipitate is Ag2 CrO4. Okay, terrible lag on this pen. Okay, perform a calculation to show whether a precipitate of the silver chromate would form before all the chloride ions have reacted with the Ag plus ions. Okay, so they give us a bit of information there, what they say earlier on. They say, look, that's the total volume at the endpoint. So you've got 20, that's 52.5. 25 comes from the seawater, 26.5 comes from the silver nitrate added, and then the final 1 centimeters cubed is the indicator that they've added. So that's the final concentration. So what we need to do here, we need to work out the concentration of the chromate ions at in that solution. Okay, we need to work that out. So it tells us that the concentration of the, well, we need these bits of information up here. It tells us you had potassium chromate there, and the concentration of that is 0.05, and we know that the volume is 52.5. So how are we going to work out the concentration of the chromate ions? Well, we're going to do moles over volume. Let's do that. Right. So the moles of chromate added, let's write that down first. The moles of right, that's going to be equal to the concentration of the chromate multiplied by the volume. Okay, so the concentration of the chromate, they told us in the original thing was 0.25 moles per decimeter cubed, and the volume they add is 1 minute. Okay, this is the last question. I'm having a few problems with this whiteboard, so I am going to open a new whiteboard up. Give me a second. Okay. Okay, hopefully this is going to solve that problem. Right, so let's say here, right, the concentration, so the moles of the chromate, that's better, is equal to the concentration of the chromate indicator multiplied by the volume. Right, the concentration of the chromate was 0.25, and we added 1 centimeter cubed of it. So that gives us the moles of chromate we have added is 2.5 times 10 to the minus 4 moles. Right, so let's work out the final concentration of the chromate. Right, the final concentration of the chromate is equal to the moles over the volume. Now they told us well, we know the moles is 2.5 times 10 to the minus 4. And we know the volume, well, they told us it was 52.6 centimeters cubed, 52.5 centimeters cubed. So that's 52.5 over 1,000. and that is equal to 4.76 times 10 to the minus 3. Right, that's our moles of chromate. Now we need to work out, right, we know that the solid KSP is going to be equal to Ag plus concentration squared multiplied by the concentration of the chromate ions. And that has got a value of, tells us in the question, that is a very small value. It is 3 times 10 to the minus 12. Mole cubed dm to the minus 9. Okay, now we know the concentration of the chromate. We just worked that out. That's 4.76 multiplied by 10 to the minus 3. And we worked out the concentration of Ag plus in the previous question. That was equal to 1.41 times 10 to the minus 5. So let's work out the value of this product. What have we got here? Okay, and we need to see whether it is larger or smaller than the KSP value. Well, that's going to be equal to 1.41 times 10 to the minus 5 squared multiplied by 4.76 times 10 to the minus 3. Do that in a calculator, we find out the value of that is 9.35 times 10 to the minus 12 mole cubed dm to the minus 9. Now, importantly, that is smaller than this value. So that means no, so therefore, we're going to see no Ag2 plus Ag2 precipitate will be formed before all the chloride ions used up. You're going to have to add enough Ag plus to react with all the Cl minus, and then a tiny bit more afterwards in order to make the solubility, make this value bigger than the solubility product in order to get the precipitate. So you're not going to get any precipitate forming before all the chloride ions have reacted. Okay, that is the end of that paper.